So you can also put together ionic compounds using polyatomic ions. Polyatomic ions are groups of atoms that come together, and when they come together they hold a particular charge. There are groups with different charges. Some of them are interrelated, but you need to memorize these. I've provided that list for you and with the notes, and you need to memorize these. There's no easy way to say it. You have to memorize them. Quiz yourself. I might quiz you. Memorize them. Okay? One of the things that you will note, see how you have sodium carbonate here? It's the same thing to make the ionic compound. You still flip-flop, okay? So it becomes Na2CO3. However, when you have something like calcium hydrogen carbonate, where Ca is a +2 charge, and this guy has a negative charge, when you flip-flop, you must put a parentheses around that entire, around the entire polyatomic ion. Otherwise, that actually reads 32 for that oxygen and not for all of this. So parentheses in chemistry are similar as they are in math. It means that that 2 is multiplied for the entire thing. And since the entire thing is the only thing that has that charge, that's how we figure that out, okay? Now, I want to talk to you all a little bit about the differences between ionic and covalent compounds. Some of this is in future videos to come, okay? Ionic compounds are made of 2 charged atoms, most typically a metal and a nonmetal, that are held together by positive-negative attractive forces that bring them together. Covalent compounds are made from 2 nonmetals. This is where you have a sharing of electrons that are kind of like, yeah, good. It could be an unequal sharing, one direction or the other, but it's a sharing of electrons. Both of them can dissolve in water, depending on what it is. Most salts do, and the salts separate into positive and negative ions. Table sugar will be an example of a covalent compound. It does not separate. They stay intact. Okay? These have very high melting points. Their melting points for covalent compounds is usually much smaller than that. Okay? And this is what a crystal lattice looks like. So this is basically what ions look like when they're dried out and all together in a crystal. So the positives and negatives are all kind of interlaced and surrounding each other with that. Here's what I mean by that. So here's a positive charge, negative charges on all 4 directions, right? But we don't really have that necessarily with covalent compounds. They can certainly stack, and they'll stack in a certain way. But this is sort of what things look like in bulk solid here. We have to consider with covalent compounds what things look like in 3 dimensions. So, as I said, these bonds can be equally shared, which would be a nonpolar species, or unequally shared, which would be polar. Each individual molecule will have its own, well, not every type of molecule, will have its own geometry. The shape of that molecule and its polarity determine how these molecules react in large quantity. So, in other words, a cup of water or a cup of methanol. Okay? Intermolecular forces is what keeps that cup of molecules tied together, because it's not like this. Okay? Okay. Really quickly, I want to run you through how to name covalent compounds. If you have something like CO2, the difference here versus what we just did with ionic compounds is we're going to give the second, or either in the first, a prefix to tell people how many there are. So this would be carbon dioxide. Here we have 3 oxygen, so it becomes sulfur trioxide. And we do that by using this nomenclature over here as the prefixes. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. It'll be 1 through 10. This again is something that you need to commit to memory. Okay. We usually don't say mono, but since carbon dioxide is so prevalent, we do tend to say carbon monoxide with that one, so you might be familiar with that. Sulfur hexafluoride means that there's 6 fluorines there. Okay, thank you very much. Lewis dot structures come up next.